Hello everyone and welcome. Today, we're going to explore one of the most important components in electronics, capacitors. Now, you might not see them directly, but capacitors are inside almost every electronic device you use. Phones, laptops, chargers, even cars. Think of this session as a simple walkthrough. We'll understand what capacitors are, how they work, and why they're so widely used. By the end, you'll not only know the concept, you'll actually be able to relate it to real-world applications. So let's get started. Let's begin with the basics. At its core, a capacitor is a device that stores electrical energy. You can imagine it like a small rechargeable container. When voltage is applied, it stores energy, and when needed, it releases that energy back into the circuit. Now, unlike batteries, capacitors don't use chemical reactions. Instead, they store energy using something called an electric field. Here's how. When we apply voltage, charges build up on two plates. One becomes positive, the other negative, and an electric field forms between them. That field is where the energy is stored, and this is why capacitors are so useful in circuits. For example, in power supplies, they smooth out voltage fluctuations. In audio systems, they help filter signals. In communication circuits, they manage frequencies. So even though they are small, their role is huge. Now let's look at what a capacitor is made of. First, we have two conductive plates. These are usually made of metal, and they store opposite charges when voltage is applied. Between these plates, we have something very important, the dielectric. This is an insulating material, meaning it doesn't allow current to flow directly, but it allows the electric field to exist between the plates. This dielectric actually increases the capacitor's ability to store energy. Common materials include ceramic, plastic, or even air. Finally, we have connection terminals. These are the leads that connect the capacitor to the circuit, allowing it to charge, discharge, and interact with other components. So in simple terms, two plates plus one insulating layer equals a capacitor. Now let's understand how a capacitor behaves in a circuit. When voltage is applied, the capacitor starts charging immediately. Electrons gather on one plate, creating stored energy. Now here's something interesting. Capacitors allow AC signals to pass through. That's because AC keeps changing direction, so the capacitor continuously charges and discharges. But when it comes to DC current, the behavior is different. Once the capacitor is fully charged, it blocks any further DC flow. So it basically acts like an open circuit. This unique behavior makes capacitors extremely useful. For example, they allow signals to pass in communication circuits. They block unwanted DC components. They release stored energy when needed, like in power backup systems. So overall, capacitors don't just store energy. They control how energy flows. Finally, let's look at the different types of capacitors. Each type is designed for specific applications. First, ceramic capacitors. They are small, non-polarized, and great for high-frequency applications like mobile devices. Next, electrolytic capacitors. These have high capacitance and are mainly used in power supplies, but they are polarized, so they must be connected correctly. Then we have tantalum capacitors. They are compact and stable, often used in circuits where reliability is critical. Next, film capacitors. These provide high precision and low energy loss, making them ideal for signal processing and audio circuits. And finally, supercapacitors. These can store a huge amount of energy and are used in applications like electric vehicles and energy backup systems. So depending on the need, size, capacity, stability, we choose different types of capacitors. Let's quickly look at the most important capacitor specifications. First, capacitance, measured in PF, NF, or micro-F. This tells how much charge it can store. Right finger. Larger value equals more energy storage. Next, voltage rating, maximum safe voltage. Exceeding this can permanently damage the capacitor. Right finger example. A 16 volts capacitor should not be used in a 24-volt circuit. Then, tolerance, variation in actual value. A 100 microfarads capacitor might actually be 95 microfarads or 105 microfarads. Next, ESR, equivalent series resistance. Lower ESR means better efficiency and less heat. Finally, leakage current, small energy loss over time. Ideally, this should be minimal. Right finger in precision circuits, leakage matters a lot. Capacitors are used everywhere. Let's see how. First, energy storage. They supply quick bursts of power during voltage drops. Right finger. Example, stabilizing power in circuits. Next, power supply filtering. They smooth out fluctuations in DC voltage. Right finger. Without this, devices may behave unpredictably. Then, signal coupling. They block DC but allow AC signals to pass. Right finger. Important in audio and communication systems. Next, timing circuits. Used with resistors to control delays. Right finger. Example, blinking LEDs or oscillators. Finally, motor starting. They provide initial boost to start motors. Right finger. Used in fans. Compressor. Let's connect this to real life. In smartphones, capacitors stabilize voltage and filter signals. In televisions, they help maintain consistent display and sound performance. In power adapters, they smooth output voltage for safe charging. In electric vehicles, capacitors assist in power regulation and energy bursts. And in renewable energy systems, they help stabilize power from solar panels and wind turbines. Right finger. So capacitors are not just components, they are enablers of modern technology. Finally, let's look at the strengths and limitations. Checkmark advantages. Capacitors charge and discharge very quickly, much faster than batteries. They have a long lifespan, thousands of cycles, and their design is simple, making them reliable and compact. Warning limitations. They store less energy compared to batteries. They are sensitive to high voltage. Overload can damage them. And over time, they degrade. This is called aging. Let's explore the main factors that cause capacitor failure. High temperature is one of the biggest threats, especially in power supplies, where heat accelerates internal chemical breakdown. Overvoltage, such as using an incorrect power adapter, can damage the dielectric layer and lead to sudden failure. Aging is another unavoidable factor. Over time, capacitors lose their effectiveness as internal materials degrade. Finally, ripple current, commonly found in switching circuits, generates internal heat due to resistance. Together, these stresses significantly reduce capacitor lifespan and reliability. Let's look at the root causes behind these failures. Overvoltage events, like power surges, can break down the insulating material inside the capacitor. Overheating, often due to poor ventilation, causes permanent internal damage. Incorrect polarity, especially in electrolytic capacitors, can result in immediate and sometimes dangerous failure. Aging gradually reduces performance as electrolytes dry out. Mechanical stress, such as vibration in automotive or industrial environments, can weaken internal connections and seals. Understanding these causes helps in designing more reliable systems. Capacitors often give warning signs before they completely fail. A bulging or swollen top indicates internal pressure buildup and is commonly seen in damaged motherboard capacitors. Leakage of electrolyte suggests that the internal seal has failed. A burning smell usually points to overheating or insulation damage. You may also notice circuit malfunctions, such as devices not powering on properly. Unstable output, like flickering screens or inconsistent voltage, is another key indicator. Recognizing these signs early can help prevent larger system failures. To ensure long-term reliability, proper prevention methods are essential. Always select capacitors with the correct voltage rating, ideally higher than the circuit requirement, to avoid stress. Effective cooling, such as using heat sinks or proper airflow, helps maintain safe operating temperatures. Ensuring correct polarity during installation is critical, particularly for polarized capacitors. Using high-quality components from trusted manufacturers improves durability. Finally, a well-designed circuit layout minimizes electrical stress and enhances overall system performance. Capacitors are essential for stable and reliable circuits. Choosing the right type and using proper design helps prevent failure. Thank you for watching. If you found this helpful, don't forget to subscribe to Play Learn Planet for more easy-to-understand electronics content. See you in the next video.